Hello and welcome to part 1 of episode 3 of QE for Problems. Today we'll be looking at problem 3 from the Project Euler problem set, which wants us to find the largest prime factor of the large number shown there. So the reason this is split into two parts is we'll actually be looking at two separate algorithms. So the first algorithm we'll look here now in part 1 is the trial division, which is probably the most intuitive and simplest algorithm. It does kind of exactly what you probably would do using pen and paper, and that is just to try different factors, try different numbers, see if it's a factor, and if it is, note it down. If not, move on to the next and try that. So if we start with, say, a smaller number, n equals 100, so we're going to try and factorize the number 100. Because we're doing trial here, we're going to be actually doing a loop solution to try different numbers. So we're going to have a variable p here, which just starts as an empty list, and it will be used to store our prime factors found so far. And then our starting point will be 2, as it is the smallest prime number. Of course, everything's divisible by 1, so no point starting there. So if we run that and set those, essentially what we want to do is check is a number evenly divisible by the number that we're trying, i.e. d. So we do n mod d, and if the remainder is 0, that means it's evenly divisible, which means it is a prime factor or a factor. So what we'll do is, if that is the case, we will join that factor on to our list of factors, and we will then reduce n by that factor. So if we do n divided by d, we're essentially removing d from n and then reassigning that back into n. And we just want to continue repeating that until this condition on line 4 is no longer true. So if we run this again, it's still true, so we join on 2 again and then reduce it now to 25, and now if we do it again, you see it's actually false because 25 is not evenly divisible by 2. In that case, we then move on to our next number, so that'll be d plus sine 1, which basically increments d by 1, so now d is 3, and then we repeat these steps, and then we'll move on to 4, and then 5, etc. So essentially then, to do this easily, we can use the while control construct. So usually in Q we want to avoid using this where possible and use the while overload of the over accumulator. But we have to maintain the state of n, p and d, which can actually be quite cumbersome when using the over, because you have to do it in a function form, which means you have to continuously pass these values back into the over and then indexing to get these values, which isn't not really a clean or easy solution, I don't think. So this is exactly why Q does provide these constructs. I think for cases like this where there is no better way kind of to do it. So we're just going to copy in what we had here in line 4 to 6. So the while control construct takes as its first argument the predicate check. Essentially, if it's true, continue the loop, and as soon as it's false, the loop exits. So this is our inner loop of the two loops we'll be discussing. This will handle the current value of d and will continuously go until the current value of d is no longer a factor. So if I reset these values and then run the loop, and if I check my n, you see it's now 25, so that was the point where it's no longer divisible. And if I check my p, it's got the 2 2's. So we now need an outer loop to handle this checking different values of d. So if I say while our condition is that the value of d is less than or equal to this s. So this s is actually the square root of our original number. So it can be shown, and you'll see it in notes which are made available on the SharePoint, and I'm actually going to create a Git repo as well with all this code and the episode notes. So the proof will be in there. However, any number, any composite number will always contain a prime factor below its square root. So if we set s equal to ceiling of square root of n, so the reason we're using ceiling here is to round up. because we can't round down. We have to go up to the square root. So if the square root's fractional, we'll have to just basically go up to the next number, the next whole number up. So run these again. So we want to go until d is essentially this loop will terminate whenever d is greater than this value. Then we want to do what we've done before, have this inner loop, and then once that is done, we need to increment our value of d just like we did before. And that's essentially it. So if I reset the variables here and then run the loop, and getting a mismatch type, oh sorry, there's a missing semicolon. So run that, and then if I look at n, you see the value of n is now 1, i.e. it's been completely factorized. And if I look at p, and you can see here it's got the prime factorization of 100. So if I was to say take these numbers and do a product of all of them, you can see it gives us 100. So there is a small improvement we can make here. So if I actually instead use the 0n bang to print out the value of n at each iteration of d. So let's fix that. So if I reset these and then I run this loop, you can see actually here that it had a value of 1 for a lot, most of the iterations, but we can actually terminate as soon as the first value of 1 is found. So in here on line 5, the actual outer while loop condition, I can actually just check to make sure n is still greater than 1, because if it's equal to 1, essentially we can stop the iteration. So if let me just clear my output and reset the variables and run this again, you can see now that it only iterated until n was 1 and then stopped. There is the case that n, by the time we get up to d equals the square root, n is still greater than 1, in which case that is because n itself is a prime number which couldn't be factorized any further. So we need to check for that condition and actually join n on to the list of primes that we actually produce, because it itself is a prime factor at that stage. So we can do that easily using an ifs. So if n is greater than 1, then we want to return p join n. If not, we just return p. And that essentially is our first function. So if I go over here to pfact1, the only difference here is I've added this extra statement to check if the given value that trying to factorize is less than 2, then we just return it, because we start at 2 here in this algorithm, which means that anything less is not going to actually work for it. But everything else is pretty much the same, just where n has been replaced with x for the functional version. So the actual then solution would be pfact1, pfact, I can spell that right, 1, and then if I grab, let me just get the actual number that we were trying to factorize. So if I run that, you can see here now these are the factors, the prime factors of the number in question, and then the question wants the max, so essentially we just do max on that, and that's our answer. So we can actually make another improvement to this function. So if you notice, we're checking all the numbers up until the square root, so we're checking 2, 3, 4, 5, 6, etc. However, once we check 2, all the even numbers like 4, 6, they can actually all be factorized into 2, which means once we check 2, we no longer need to check any of those numbers because they've already been covered. And that's the same with 3. We don't need to check 6 or 9 because those can be factorized and they, have the factors of 3. That means we only need to actually check the prime factor or prime numbers up until the square root. So to generate the prime, I've just pasted in this line here. This function essentially, so instead of having this here, I'm going to just put s, just keep things simple. It'll generate the prime numbers up until the input. So you can see the input here is the square root of 100, which will be 10. So this gives us all the prime numbers up until 10. How this function actually works is described in another blog post on KX community, so I will link that below. It's described quite well there, so I'm not going to actually describe how this function works here. But essentially I have it in a math library as well, so once I make this code available on the Git repo, you can see it there too. But anyway, we only need to check, yeah, these four numbers essentially. Of course, whenever this number is bigger, there will be more numbers here, but it will still be a lot less. So for a large number, we're going up to its square root. So for this number in question here, if I do square root of that, you can see we would actually we'd have to check all the numbers up until this, rather than just checking the primes, which is going to be a lot less numbers to check. So it kind of removes a lot of redundancy in the checking process. Again, we're going to stick to using our while constructs because the overforms, yeah, you still have to maintain that state, and it's quite untidy looking and actually less performant, as I found. So we have our list of primes, and then we have some maximum that we want to go up to, i.e. the count of that list. We then have a indexing variable, so you'll see this is kind of very similar to what people would do in other like C languages, lippy languages. Unfortunately, I think it's just the best way to do this particular problem. And I couldn't find a nice solution in Q without using the while. And then P, as before, is our list to keep our variables, our prime factors so far. Essentially, then we just want to do what we've done before. We have the outer while loop. Now our condition has changed to is I less than the count, i.e. we only want to go over this list here, so we don't want the ID to pass the count of this list. And we also have our n is less than or equal to 1, as we had before. So our first line is D is the current number in the primes that we're at. So for the very first iteration, it's going to be 0, which is going to be the first term, which is going to be 2, and then I'll move on to 3, then to 5, and 7. And our inner while loop is essentially as we had it before. So it'll be 0 equals n mod D. If that's true, then we want to say that P join equals to D, and we want to reassign n to n div D. So that's the exact same as we had before. There's no change there, and then this is just an incrementing value of I then to move on to the next prime number to check. So if I reset everything here, D, and just remove the space and run this, and then I check my value of P, you can see it still has the prime factors as well, so that's correct. And yeah, so that essentially is a more efficient algorithm. It has less to check. So if I look at P factor here, this has this implemented. Again, we have that check for less than 2, all the preset variables, and then the while loop we just discussed where x, n has just been replaced with x for the function form, and then remember this last check as well, that if n is itself prime, it needs to be joined on to the actual list of primes. But yeah, that's essentially the best kind of form of that trial division solution I could find. So if I run this now, I can still get the same solution. Just looking at the performance here now of the two solutions, the two forms of the trial division algorithm. So this is running 100 times for the number in question. So if I do that, you can see the prime factor. So if I run this, the performance test, you can actually see that P factor 1 is a lot more efficient for this particular number, definitely in terms of memory and time. However, let's look at this is just a number with a large factor. So if I run pfact, you can actually see here it has a very large prime factor. So if I run the performance test, and I'm only run this 10 times because you'll see the performance of pfact 1 is actually a lot less. It is not great. So there's 3 seconds just for 10 times. So you can see here that pfact 2 is actually a lot more efficient in time than pfact 1, because it just depends on the number. Pfact 2, the actual effort of generating the primes has to kind of be worth it, so that is dependent on the number that we're actually factorizing. And you can see here there's a large prime. This is just a large prime where we'll have to basically check everything. It couldn't do this exit an early thing where n is equal to 1, like it would never get to that point because it's always going to be prime right up until the very last check. So it has to go through the whole list of numbers. And if I set that, so you can see if I run pfac1 here, it just returns me the number. But if I actually run the performance test here, you can see again, pfac2 is a lot more efficient. So in general, pfac2 is going to be better, but for the actual number in the question, pfac1 turns out to be better. But yeah, that's it for part 1. So in part 2, we'll be looking at Pollard's row algorithm. So yeah, please check that out. And yeah, thanks for watching. Please post any of your solutions below. Thank you.